Hello, we are Team 7, the automated bartender team. The members are in the group are myself, Sam Lotto, Brad Rogers, and Sam Burtz. We decided to do the automated bartender because we wanted to pick something that would automate one of the functions performed in the service industry. And in our limited time, we figured that the automated bartender would be one of the things that was mechanically possible.
So the main board is basically the board on which all of our smaller modules are mounted. It also interfaces with the Altera board, as you can see from the picture here. Um, it contains two logic level shifters, which take our 5-volt signals from our sensors and converts them to 3.3s that can be handled by the Altera. And it also basically just routes all of the signals out to those RJ45 connectors on the side and routes the signals to the boards that are mounted on top of it. Um, the main purpose of this board was, since it's very large, it's more expensive to construct. So by constructing this board and then smaller modules that mount on it, we were able to save cost when reordering our boards, as we could just reorder the small boards. The power board is mounted on top of the main board and is used to deliver power to each of our motors. We did not want to draw power for the motors from the Altera board due to the large currents possibly damaging the pins. The power board takes in a 12-volt source from the wall, DC, and converts it to 6 and 12-volt output pins. The 4 pins on the top are 6 volts and the 4 pins on the bottom are 12 volts. And due to that symmetry, we were able to mount the board upside down. We did this because we ordered the wrong voltage converter, which conveniently fit in the opposite converter's package. That way we could switch the positions and flip the board and mount it upside down and still get the correct voltages to each pin.
For the stepper motor controller board, the main component was the TI DRV8811 stepper motor controller IC. The reason that this component was chosen was because it was able to handle a large range of voltages, and since we did not know how strong of a stepper motor we would need, this was a good chip. It also has very precise control for the stepper motor, which is important because we were not sure how we were going to dispense our liquids. What went wrong was there was no ground routed to the board, so we wired up a wire from the ground to the ground portion of one of our resistors to fix that issue.
The IR sensors are mounted in front of each bottle. 8 IR sensors correspond to each of the 8 bottles on the track. The sensors were originally going to be used by aiming them at the bottom of the bottles and communicating with the software when the bottle was empty. Due to varying bottle sizes and different colored liquids, the sensors only worked for very, very dark liquids. For this reason, we decided to change the application of our sensors to communicating with the software if a bottle had been removed. This way, if the track moves to a position where a bottle is no longer there, it will communicate with the software and not allow the drink to be poured from that location.
For the force/servo board, the main component on this board was a variable force resistor um, and an op amp. What we did was we created a threshold voltage with the variable force resistor, so there had to be a certain amount of weight on the force resistor for it to notice a change. What went wrong with the board was originally layout. The layout had to be changed in order to fit in the mechanical construct of our track. The main mechanical component of our design was the track, which is a piece of 80/20 with a slider attached to that. That slider is screwed into a timing belt. On top of the slider is a box that was designed to both hold the cup, hold inside of the box, hold the servo and slash force sensor board, as well as be able to mount the servo on top to push up on the nozzles for our drinks.
As far as the software goes for our project, there was a few main components. The first was the drivers. The drivers were what controlled the stepper and the servo motors, and those originally were very static and were not able to be modified very much. But due to the fact that they did not work correctly the first time. I changed them to be very dynamic, so you can send in anything from the frequency to the pulse size to the steps, and that made it a lot easier to precisely control those. The next part was the C code that's on the board itself. The C code was pretty straightforward. It essentially just controls the kind of main loop logic of the actual Bartender itself. It works pretty easily, and I've actually implemented the push buttons on the side in order to help through some of the process if things do get messed up on the board. The next part was the API backend, which was kind of a design decision that I chose to make so that way we could interface more easily with the website rather than having to interface directly with the board. And with this, I chose to make the API have a GET request that the board calls and a POST request that the website calls in order to add drinks to the website. The final part was the website itself. The website itself is where the user can create drinks and add them in. And the website allows for variable customizability by just additions to a JSON file, which kind of allows the user to kind of customize what they want based off of what beverages are currently in the Bartender themselves. So your first point of contact with the automated Bartender is going to be the website. As you can see, we have 2 drinks preloaded in here, a rum and coke and a vodka lemonade. So if I want to go and order a drink, I can come onto here and I can click order drink. And now I've ordered that drink and it's added onto the queue. So if we come over back to the actual machine now, the machine itself is going to wait for the glass to be placed so that way it doesn't dispense the liquid into nothing. So once we place this glass down, it's going to move to the dispense locations. This is vodka and this is lemonade in our situation. So it's going to go and it's going to dispense 1 shot of the vodka, and then it's going to dispense 4 shots of the lemonade because that's how much it would need to fill up the rest of the 8-ounce glass that we selected. Now, once the drink is back in this original location, it's going to wait until we remove this glass in order to continue making drinks. Now, as you can see, we did remove this bottle, the lemonade bottle. So what will happen now is when it tries to make another vodka lemonade, it will not actually dispense the lemonade because there's nothing there to dispense. So if we remove our glass, say we drank this glass, now we put another glass back on, it should do the same thing again because I had already queued up a second vodka lemonade for the purposes of this demonstration. So as you can see, it still dispenses the vodka properly, but since there's no bottle here in the lemonade, it does not dispense anything.
The lessons that our group learned while doing this project was first, to modularize boards to allow for efficient redesign and testing. Second, to design test setups to allow testing of components before full fabrication. Third, make software as customizable as possible. Fourth, overestimate time necessary to complete tasks to allow for complications. And finally, to develop your project in parallel to maximize time and efficiency.